Steel structures are usually fabricated from preformed, standard open or closed road sections, or from sections fabricated by welding together steel plates, or combinations of standard sections. The cross-sectional shape of standard sections is chosen to suit particular structural requirements, and standard sections are available in a range of sizes and in different qualities of steel. Standard open sections include universal beams, with depths varying from 203 millimeters to 914 millimeters, proportioned to have a much greater depth and breadth, so as to resist bending efficiently about one axis. Universal columns, stockier members with depths varying from 152 millimeters to 356 millimeters, proportioned so as to resist efficiently, primarily compression loading. Channel sections, and equal and unequal angle sections. Standard closed sections are essentially tubes which may be square, rectangular or circular in cross-section, with overall dimensions varying from 20 millimeters to 450 millimeters. Some of these sections are the basis of other standard sections, such as castellated beams and structural tees. The basic component of fabricated or built-up sections is usually steel plate, which is available in a wide range of thicknesses and may be used to form plate girders and indeed structures in their own right, such as tanks, bunkers, hoppers, and so on. Steel sections and plates are available in a range of strengths of weldable structural steels, most common of which are BS 4360, grade 43, mild steel, and grade 50, high-yield steel. Higher strength steels are available for special applications, but these are usually available only in the form of plates. Strength may not be the sole criterion for selecting types of steel. For example, resistance to fracture is important for tension regions, particularly at low temperature and for thick welded sections.
Yeah, raise this with me.
The fabrication process normally starts with the receipt of an order which will probably involve the company undertaking both fabrication and erection of the steelwork in question. The order will include contract drawings, specification requirements, quantities, terms and conditions of contract. There may be a requirement for some detailed design by the fabricator, particularly for connections in steel buildings. On receipt of such an order, the fabricator will start to plan the progress of the job through his works and its subsequent delivery to site. This planning results in a program of work, often produced with the aid of a computer. It allows for ordering and delivery of material from steel mills or stockholders, preparation of fabrication drawings, as well as the actual fabrication process in the works, and the application of protective finishes prior to dispatch and delivery to site.
And that doesn't no. So, from your point of view,
Careful and realistic planning is essential to the success of the fabrication operation and will endeavor to ensure optimum use of works facilities and capacity, bearing in mind other active or proposed contracts.
Triangular.
There is, yes. Yes, we hope we'll be able to utilize it.
It is then the responsibility of the drawing office to interpret engineers' contract design drawings and calculations, to provide the material ordering department with complete lists of all steel, fittings and bolts. For this, the fabricator usually undertakes the detailed design of any connections and produces fabrication drawings which are also used for the actual fabrication of the steelwork. Computer-aided design may be used. Whilst fabrication drawings are being prepared, a detailed schedule is produced showing how, to a given timescale, each element will progress through each of its stages of fabrication and finishing. This must take account of available equipment, the size of the element and the plant necessary to handle it, and seeks to ensure that all the fabrication facilities are used at all times. Steel from the mills may be delivered to the fabrication works by road or rail, although road is more common. On arrival, it is placed in a stockyard where it is stacked in a predetermined location, convenient for easy access and lifting by cranes. Each item of steel entering the stockyard is given an identification mark, and a record of this, together with relevant data such as grade and weight, are kept. When required, steel is moved from the stockyard into the factory. Prior to fabrication, some form of preparation may be required, particularly if subsequent painting is specified. Most commonly shot or grit blasting is used. The steel will progress first through a preheat oven. In a blast cleaning plant, the steel is bombarded by high-speed particles of shot or grit, which remove mill scale and rust to clean the surface and allow maximum adhesion of paint. Blast cleaning is closely followed by paint spraying with a prefabrication primer to protect the clean surfaces. Following this preparation, the actual fabrication process begins. During the phase in the preparation hall, the steel is moved around by overhead travelling cranes. For typical building frame steelwork, the sections are first sawn to length by a circular cold saw, the speed of cutting being automatically adjusted to suit changing material dimensions as the saw passes through the workpiece. This cutting to length, which may be within a squareness of 0.2% on the depth of cut, will be automatically operated through a computer-produced tape. Smaller sections may be cut by a smaller saw. Drilling is also automatically controlled by computer-produced tape, and the provision of multi-heads enables a number of holes to be drilled simultaneously at each transverse section. Alternatively, holes may be punched more rapidly, and this is usually permitted in thinner sections. Modern machines operate with a minimum of material distortion. Punched holes are normally only used for secondary members, angle cleats or gussets, in material up to about 12 millimeters in thickness. Cropping shears, which operate in a similar way, can be used for cutting relatively light angles, flats, T's and rounds. The shearing of plates up to about 25 millimeters thick may be carried out by guillotines. Complex or curved shapes are obtained by the use of an oxygen and acetylene flame cutting system. This operation can be controlled by an optical head following an outline drawing on paper or by a numerically controlled computer tape. The simultaneous use of a number of heads allows edge preparations to be made for plates which are to be welded. Flame cutting can also be used for profiling tubular sections. In circumstances where sawing or flame cutting is not sufficiently accurate, the ends of sections are milled. This will only be necessary when full end bearing is required, as in the case of some column splices. Machining may also be necessary on column slab base plates. The forming of plates into shapes may be accomplished by the use of presses, having a variety of sizes and proportions. The commonly used brake press handles material which is narrow compared to its length, and can produce, for example, the trapezoidal-shaped trough sections used to stiffen bridge decks. Other hydraulic presses can be used for a variety of purposes. Cylindrical and conical shapes may be produced by the cold rolling of steel plates. Rolling machines comprise two lower rows which are fixed in position and a single larger upper row which is adjusted in height to suit the thickness of the plates and the diameter of roll required. Modern rows can accommodate plates up to 100 millimeters thick. The resulting tubes may be used, for example, as the tubular legs and bracing members for offshore drilling platforms. For long-span girders, where the requirement to resist shear is not high relative to the bending resistance required, it has been found to be economical to increase the depth of standard rolled beam sections. This can be achieved by the formation of castellations in the beam webs by flame cutting. The two cut halves are subsequently welded together again to produce a deeper girder with hexagonal holes in the webs. It is occasionally necessary to weld additional plate material into the hexagonal holes at either end of the girder to enable it to sustain the end support reactions. In manual metal arc welding, an arc can be struck from a wire electrode onto parent metal. In its practical realization as the manual metal arc process, a covering extruded onto the rod melts to protect the weld zone from atmospheric contaminations. The end of the electrode melts and adds filler metal to the weld pool. Manual metal arc welding will join most steels from 3 millimeters thickness upwards. This flexibility is used in both workshop and site welding. Welding produces full-strength joints without excess metal in the form of overlaps, screws or rivets. The electrode is held in an insulated holder and manipulated manually by the skills of the welder. For longer runs, the semi-automatic metal inert gas, MIG welding, or gas-shielded CO2 system can be used. In this case, the electrode wire is fed from a continuous reel to a trigger-controlled, hand-operated gun. The arc is protected by a gas shield of either an inert gas or CO2 to keep the oxygen in the atmosphere from reacting with the molten weld pool. In submerged arc welding, the other main welding process, a continuous wire is fed from a reel with a granular flux covering the arc. This is an automatic process and is particularly useful for long lengths of weld in fabricated plate and box girders and for production line work such as structural panels for bridges. It has the advantages of a hidden arc and high deposition rates with deep penetration. A good surface finish is normally obtained. In connecting plates, a master template is produced to determine hole positions. Identical plates are then punched in batch production. When all the elements and fittings have been fabricated separately, they're brought to the assembly bay for completion. Assembly is accomplished using either welding or bolting. For bolting, ordinary bolts, which are normally hand-tightened by spanners, or high-strength friction grip bolts may be used. The latter transfer load by friction between the joint plates. A predetermined bolt tension is induced, for instance by tightening using a torque wrench. Welding, using the processes described previously, generates heat which may cause distortion. This can be controlled by presetting components or by preheating. It is frequently helpful for the assembly to take place in a jig, with the component held together by tack welds. Tack welds are short lengths of weld separated by relatively long gaps which temporarily hold the component together. The order of completing the welds is arranged to minimize distortion by balancing the weld disposition. Clearly, the use of jigs is most economical when they can be used for a large number of elements, since they're relatively expensive to provide. Quality control starts with the designer, the drawing office, and the material buyer. All fabrication operations depend on the choice of fabrication details generated and on the material used. Regular inspection and quality control ensures that all material can be identified with respect to grade. Material is tested ultrasonically for laminations at points where major welding is to be carried out. Weld inspections and tests are carried out both during and on completion of welding to ensure satisfactory mechanical properties and freedom from defects in the welded joint. Welding electrodes are correctly stored and identifiable. Identification marks and erection marks are clearly visible. Measuring devices are regularly calibrated. Some structures or critical parts of structures may require check erections at the fabricator's works. Whilst this is expensive, it may highlight problems which will be impossible or expensive to rectify on site, particularly if the site is overseas. Following fabrication, much steelwork is paint sprayed manually or automatically, whether it's been blast cleaned or not. A variety of paint finishes may be specified, ranging from one-coat primer to multi-coat special paint treatments. For particular applications, such as for overhead transmission line towers, the structural steel members are likely to be hot-dip galvanized or metal sprayed. It is particularly important that care is taken in handling steelwork to minimize damage to the coating. Following painting and drying, fabricated steelwork is consigned to a storage area where it will be stacked in a location and in such quantities and sizes as to facilitate its loading onto lorries for transportation to site. If large areas are not to be devoted to storage, transport must be programmed to be available following completion of fabrication. Rapid delivery also minimizes the risk of damage to the steelwork itself or its protective coatings. Transportation of very large items of fabricated steelwork may require prior arrangements to be made with police and/or highway authorities. Planning for this should be made well in advance. Care, attention to detail, and overall efficiency in the fabrication of structural steelwork minimize problems on site and result in more rapid erection and greater cost efficiency.